Cantorix. In the deepest reaches of time, when all the stars have died and galaxies have scattered into the void, when even the memory of light has faded into legend, there exists one final ember in the cosmos. A black hole. Not one of the great giants that once devoured stars at the hearts of galaxies, not one of the stellar corpses born from supernovae in the universe's youth. This is something far stranger, far older, the last black hole. The final gravitational monument to everything that ever was. It floats alone in darkness so complete that darkness itself seems bright by comparison. Around it, space stretches in all directions, expanding, cooling, dying. The universe has grown so vast that light from one edge could never reach the other, even given eternity. And yet, this black hole glows. Faintly. Impossibly. Against every intuition we hold about these cosmic predators, it emits light. Not reflected light, not captured light, but light born from the quantum fabric of space-time itself. This is Hawking radiation, the whisper of a dying giant, the universe's last conversation with itself. This black hole is not eternal. Nothing is. And when it finally evaporates, when its last photon streaks into the endless dark, the universe will cross a threshold from which there is no return. This is the story of that crossing, the story of the last light, the story of how everything ends, not with violence, but with a whisper so quiet it makes silence seem loud. The Legacy of Darkness. 2.6 Hoeks. To understand this final moment, we must first understand what came before. We must walk backward through the ages of universal death, through epochs so long they make the entire history of humanity seem less than a blink. Trillions of years ago, in what cosmologists call the stelliferous era, the universe was alive with light. Stars burned in their billions of trillions. Galaxies wheeled through space like islands of fire. Planets formed and died. Life, perhaps, flickered briefly on countless worlds before being snuffed out by time and entropy. But even then, the end was written into the fabric of reality. The universe was expanding, driven by dark energy, pushing everything apart. Stars were being born more slowly than they were dying. Hydrogen, the fuel of stellar fusion, was being locked away in dead stars, white dwarfs, neutron stars, and black holes. 10 trillion years passed, then 20 trillion, 50 trillion. 100 trillion years after the Big Bang, the last natural star flickered out. The stelliferous era ended not with a bang, but with a dim red dwarf, cooling slowly into a black dwarf, a stellar corpse so cold it would be invisible against the cosmic microwave background. The universe entered the degenerate era, an age of slow decay. Galaxies, no longer held together by the mass of living stars, began to dissolve. Stars were ejected into intergalactic space through gravitational interactions, scattered like ashes. Some fell into the supermassive black holes at galactic centers. Most drifted alone, cooling, darkening, becoming indistinguishable from the void itself. The temperature of space approached absolute zero. Matter itself began to decay. Protons, once thought eternal, started to dissolve through quantum tunneling processes so rare they take 10 to the 36 years to occur. Slowly, inexorably, the very atoms that made up the stars and planets, the atoms that once made up us, came undone. Even dead stars were not immune. White dwarfs and neutron stars, having exhausted their heat and lost their protons, faded into what physicists call black dwarf supernovae, or simply evaporated into photons and neutrinos, scattering into the growing emptiness. After 10 to the 40 years, a number so large it has no meaning in human terms, only black holes remained. The universe had entered the black hole era, an age where gravity's final monuments were the only structures left. They dominated the cosmos, not through violence, but through sheer persistence. Everything else had decayed, dissolved, or been consumed. But black holes too are mortal. They leak, they evaporate, they die. And as the eons passed, 10 to the 50 years, 10 to the 70, 10 to the 100, even the great supermassive black holes at the centers of ancient galaxies began to shrink. One by one, they winked out of existence, each leaving behind a final flash of gamma rays so powerful it could sterilize a galaxy if any galaxy still existed to sterilize, until only one remained. The last black hole. This final black hole is not particularly large, perhaps a few dozen solar masses, perhaps less. Its exact size doesn't matter anymore because there is nothing left to compare it to. It exists in a universe so empty that calling it a universe seems generous. In every direction, space expands faster than light can cross it. The cosmic microwave background, once the afterglow of creation, has been stretched by expansion into wavelengths longer than the observable universe itself. The temperature of empty space has dropped to a billionth of a degree above absolute zero. This black hole should be perfectly dark. According to classical physics, nothing can escape a black hole's event horizon. Light, matter, information, all fall inward, compressed toward the singularity at its heart, never to return. But quantum mechanics tells a different story. In 1974, Stephen Hawking discovered something extraordinary. He found that black holes are not perfectly black. At the quantum level, the violent curvature of space-time near the event horizon creates particle-antiparticle pairs from the vacuum itself. Most of these pairs annihilate immediately, but occasionally, one particle falls into the black hole while the other escapes. From outside, it looks like the black hole is emitting radiation. Hawking radiation. Thermal radiation with a temperature inversely proportional to the black hole's mass. For a large black hole, this temperature is extraordinarily low, far colder than the cosmic microwave background. But as the black hole loses mass through this process, it shrinks, and as it shrinks, its temperature rises. The process is glacially slow at first. A black hole with the mass of the Sun would take 10 to the 67 years to evaporate completely, a span of time so vast that the current age of the universe, a mere 13.8 billion years, is less than a rounding error. But time is something this universe has in abundance. The last black hole has been evaporating for an unimaginable duration, longer than it takes for protons to decay, longer than it takes for quantum tunneling to transmute the cores of dead stars. It has been shrinking slowly, atom by atom, particle by particle, for so long that forever seems like an understatement. And now, after 10 to the 100 years, a Google years, a time span that makes eternity feel brief, it has shrunk to the size of a mountain. Then, a house, then a car. Its temperature has risen from near absolute zero to the warmth of a spring day, then to the heat of a star, then to temperatures that would vaporize atoms, that would tear apart nuclei, that would shred the fabric of matter itself into a soup of quarks and gluons. The black hole is no longer dark. It glows with a fierce ultraviolet light, then with X-rays, then with gamma rays. It is a tiny, brilliant beacon in an ocean of darkness so profound that darkness is too gentle a word for it. Around it, space is no longer flat. The curvature becomes extreme. Quantum effects dominate. Virtual particles boil off the event horizon in increasing numbers. The black hole shivers, fluctuates, becomes less like a classical object and more like a quantum ghost, something between existence and non-existence. Time itself behaves strangely here. Near the event horizon, time dilates so extremely that an outside observer watching the evaporation would see the process accelerate exponentially. What took Googles of years to bring the black hole to this point will take only moments more to finish. The black hole weighs as much as a mountain, then as much as a person, then as much as a grain of sand. Its event horizon shrinks to the size of an atom, then a nucleus, then smaller, smaller than anything with a classical size. Its temperature has reached the Planck temperature, 10 to the 32 degrees Kelvin, a heat so intense that the very concepts of space and time begin to dissolve. At this scale, quantum gravity takes over. The equations of general relativity break down. We enter a realm where physics as we understand it ceases to apply. And still the black hole shrinks. Still it glows brighter. The Hawking radiation becomes a torrent, a storm, a tsunami of energy pouring out from a point in space almost too small to exist. The universe holds its breath. In the last microsecond of the last black hole's life, more energy is released than in all the preceding Google years of its evaporation combined. The event horizon collapses. The singularity, if it ever truly existed, vanishes. And in its place, there is an explosion. Not an explosion in space, but an explosion of space. A burst of gamma rays, neutrinos, and gravitational waves so intense it briefly recreates conditions not seen since the Big Bang itself. For a fraction of a second, the temperature at that point in space exceeds anything that has existed since the first moments of creation. Particles and antiparticles materialize and annihilate in a cascade of quantum violence. The vacuum itself seethes with energy, with possibility, with the last gasp of structured existence. And then it ends. The explosion fades. The particles disperse, flying outward at nearly the speed of light into a universe so empty they will never encounter anything, ever. The gravitational waves ripple outward, carrying the news of the black hole's death to no one, to nothing, to nowhere in particular. The final photon, a gamma-ray photon born in the last instant of the black hole's evaporation, races into the void. It is the last light the universe will ever produce. The last electromagnetic radiation born from the last available energy gradient in all of reality. It travels alone through expanding space. There are no atoms left to absorb it, no eyes to see it, no instruments to measure it. It simply is, a solitary quantum of energy propagating through infinite emptiness. As it travels, the expansion of space stretches its wavelength. The gamma ray becomes an X-ray. The X-ray becomes ultraviolet. Then visible light, blue, green, yellow, red. Then infrared. Then microwave. Then radio. Its wavelength stretches to kilometers, then light years, then longer than the distance between galaxy clusters in the ancient universe. Eventually, its wavelength becomes longer than the observable universe itself. At this point, does it still exist? Is it still a photon? Or has it dissolved into the fabric of space itself, indistinguishable from the quantum foam that underlies reality? There is no one to answer that question. The universe is now in what cosmologists call the dark era, though even that name suggests more structure than actually exists. There are no eras anymore, no epochs, no ages. There is only expansion and cooling and the slow, steady march toward maximum entropy. The temperature of space has dropped to the d-Sitter temperature, a value so close to absolute zero that it makes the coldest places in the old universe seem like furnaces. This is the temperature dictated by the cosmological constant, by dark energy, by the expansion of space itself. Nothing happens anymore. Nothing can happen. Every energy gradient has been exhausted. Every particle is separated from every other particle by distances so vast that they exist in causally disconnected universes. Information can no longer travel between any two points. Time loses its meaning when nothing changes. This is heat death. Thermodynamic equilibrium. Maximum entropy. The end state that the second law of thermodynamics has been driving toward since the moment of the Big Bang. The universe has become perfectly smooth, perfectly dark, perfectly still. And in this stillness, there is a strange kind of peace. We who lived in the early universe, in the brief flicker of the stelliferous era when stars still burned and life was still possible, often feared the end. We imagined it as tragedy, the death of meaning, the extinction of purpose, the final extinction of everything we held dear. But standing here at the end, looking back across the incomprehensible gulf of time, the end looks different. It looks like completion, like a story told in full, every chapter written, every arc resolved, every theme explored to its ultimate conclusion. The universe was never meant to last forever. Nothing is. The same laws that allowed stars to form and life to emerge also ensured that everything would eventually end. Entropy is not a villain. It is not a cosmic mistake. It is simply the direction of time, the arrow that points from order to disorder, from energy to stillness. And in that stillness, there is no suffering, no loss, no fear of what comes next, because there is no next. Time itself has effectively stopped. The universe has reached its final state, the equilibrium point it has been approaching for 100 Google years. Is this death? Perhaps. But it is also transformation. The black hole did not die. It transmuted its mass into energy, into light, into the very fabric of space-time itself. It returned everything it had consumed across the ages back to the universe in the most democratic way possible, as pure radiation, as information, as possibility. Every atom that ever fell into that black hole, every star it consumed, every particle of dust that crossed its event horizon was not destroyed. It was transformed. Scrambled, yes. Encrypted in the quantum information of Hawking radiation, yes. But not gone. The information was preserved, released back into the cosmos in the final explosion. This is what black holes do at the end. They are not just cosmic predators. They are cosmic recyclers, taking the structured matter of the old universe and returning it as pure, democratic energy to the new equilibrium. In the old universe, when stars still burned, philosophers asked whether existence had meaning. They wondered if life mattered in a cosmos destined to die. They struggled with the apparent futility of building, creating, loving, when everything would eventually be erased. But meaning was never dependent on permanence. A song does not lose its beauty because it eventually ends. A story is not meaningless because the final page is turned. The fact that the universe has reached its final state does not negate the 13.8 billion years of structure and complexity that preceded it. Stars shone, galaxies formed, planets coalesced from dust and gas. Life emerged, flourished, asked questions, sought answers. Consciousness arose from unconscious matter and looked out at the cosmos in wonder. All of this happened. All of it was real. All of it mattered, even if nothing remains to remember it. The last black hole was the final witness to all of that history. For a Google years, it stood alone, holding in its quantum memory the information of everything that had ever fallen into it. The light of long-dead stars, the atoms that once formed planets and people and dreams. When it finally evaporated, it released that information back into the universe. Not in a readable form, perhaps. Not in a way that any future intelligence could decode, but it released it nonetheless, fulfilling the fundamental principle of quantum mechanics that information cannot be destroyed. In this way, the last black hole's death was not an end, but a return, a giving back, a final gift to the cosmos that created it. And what of the universe itself, now in its state of maximum entropy? Is it truly dead, or is it simply waiting? Epilogue. Echoes in the void, 20 Wangchaozi 23.UH. In the empty universe, in the silence that followed the last light, something strange persists. Quantum fluctuations. Tiny, random variations in the energy of the vacuum itself, permitted by Heisenberg's uncertainty principle. They are vanishingly small, far smaller than an atom, far briefer than the lifetime of a particle, but they are there. The vacuum is never truly empty. Even in the darkest era, even at the de Sitter temperature, the quantum foam that underlies space-time continues to seethe with virtual particles appearing and disappearing in balanced pairs. Energy is borrowed from the vacuum and immediately repaid, creating no net change but ensuring that perfect stillness is never quite achieved. And in a universe with infinite time, or something approaching it, even the most improbable events become inevitable. Quantum tunneling allows for the spontaneous appearance of particles, even complex structures, from the void. The probability of such events is unimaginably small, but given enough time, unimaginably small probabilities approach certainty. Some physicists speculate that in 10 to the 10 to the 56 years, a number so large it cannot be written with all the atoms in the old universe, a quantum fluctuation could create a new Big Bang. A bubble universe nucleating from the void, inflating, creating its own space and time and laws of physics. Others suggest that Boltzmann brains, conscious observers formed by random fluctuations, might briefly materialize and vanish, experiencing a single moment of awareness before dissolving back into the foam. Still others propose that the universe has not truly reached its final state. That dark energy might evolve, causing the expansion to accelerate or decelerate in ways we cannot predict. That the equations of quantum gravity, still unknown to us in the 21st century, might permit transformations we cannot imagine. These are speculations. Dreams, perhaps, from creatures who lived in the bright, early universe and could not quite accept that endings are final. We do not know what happens after heat death. We cannot know. The universe in that state is so far removed from the conditions under which physics was formulated that our equations may not apply. But in another sense, it does not matter. Whether the universe remains in equilibrium forever, or whether new universes bubble up from quantum foam, or whether something entirely unexpected occurs, the story of our universe, the universe of stars and galaxies and black holes, is complete. The last black hole evaporated. The last light faded. The final energy gradient was exhausted. Entropy reached its maximum. The cosmos fulfilled the destiny written into its laws from the moment of creation. And in that completion, there is a kind of perfection. Not the perfection of preservation, but the perfection of wholeness. Every possibility explored, every configuration tested, every story told. The universe began with a burst of light and energy, a quantum fluctuation that inflated into space and time and matter. It ends with a whisper, a final photon stretching into infinite wavelength, a last black hole returning its borrowed mass to the void. Between those two moments, the beginning and the end, everything happened. And that, perhaps, is enough. When the last black hole breathed its final light, the universe fell silent, not in death, but in completion.